Water is the most abundant liquid on Earth, and the oceans thus certainly drags one's attention. But the ocean by itself has always been intriguing to all of us, especially the apparently chaotic generation and destruction of waves. Understanding this natural process helps developing more accurate studies on the influence of wave loading on oil rigs and coastal defenses, capsizing the ships in heavy seas, or the action of breaking waves on stationary structures, for instance. We'll start clarifying that a wave is a manifestation of an energy frictional transfer between wind and water that lead to shear forces on the water surface. This water acquires a given velocity proportional to the curvature of the wind's velocity profile. The combination of these chaotic particle movements create a generally circular motion in the particles of a given water section, which are called ripples. Many factors affect them, but the continuous effect of the wind makes them grow from a few centimeters to a wave that can reach several meters.
We are going to explain the wave description given by the English mathematician Sir George Biddell-Airy. This description is valid for waves in which the amplitude is quite small compared to the wavelength, and considers an ideal bidimensional flow. The starting point is the Laplace equation. In this case, it's a variation of the continuity equation, and phi denotes the velocity potential function. To solve this, we need some boundary conditions. The first one is given by the seabed. As shown, at the seabed, the vertical velocity is equal to 0. So we have this first boundary condition. Then, as the amplitude is small, the vertical motion of the flow at the free surface is the actual velocity of the free surface. So we have this equation, where eta denotes the elevation of the free surface with respect to the still water level. The third boundary condition is given by Bernoulli's equation, assuming that the pressure at the free surface is equal to 0. These formulations constitute a system of differential equations, and we obtain two solutions. This one is for the elevation of the free surface. As we can see, the shape follows perfectly the shape of the wave function, and we can identify the wave number as 2 pi over L. The second solution is for the velocity potential function. We obtain this equation that will be useful right now in order to get velocities, accelerations, and displacements.
From the velocity potential, knowing that the velocity of the wave equals the partial derivative of v with respect to each direction, there can be extracted from left to right the displacement, velocities, and accelerations in x and z direction respectively. In these equations, there can be appreciated three components. The first one is a magnitude term, the second one is related to the shape variation with depth, and the third is a cyclic term that provides information about the phase. The first boundary condition is shown in W by substituting z by negative h, and states that at the seabed there's only a horizontal contribution of velocity. It explains phenomena such as sediment transportation. Displacement's equation describes ellipses, and having a look to the phases terms, we observe that velocities and accelerations are 90 and 180 degrees dephased with respect to the displacements. Another conclusion is the rate at which the energy of the waves is transmitted. The energy a wave possesses is the sum of the kinetic, potential, and surface tension energy of all its particles. In the case of ocean waves, the surface tension is negligible in comparison to the other two, and for AV waves, kinetic and potential energy are equal. Therefore, the total energy transmitted per unit of area is 1/2 rho g a squared. This energy will be transmitted at a certain celerity, but the important point here is that due to the amplitude of the circular patterns depending on the interaction with the solar node, the energy is transmitted faster the closer the Sol is to the free ocean surface.
When the linearized boundary conditions are applied onto the wave velocity field, the wave celerity formula is obtained. The value of the hyperbolic tangent can be approximated with respect to three different wave stages. The deep water stage, which corresponds to a depth equal or larger than half of the wavelength, so in this way the hyperbolic tangent can be approximated to 1, finally obtaining this celerity equation. The transitional water, which corresponds to a depth between half the wavelength and the wavelength over 20, and so the hyperbolic tangent will be bounded between 1 and the wave number times the depth. So the resulting celerity equation can vary between these two values. And the shallow water, which corresponds to depths lower than the wavelength over 20. In this case, the hyperbolic tangent can always be approximated to the wave number times the depth. So this beautiful celerity formula is obtained. As it can be seen, this celerity is only determined by the depth and not by the period. All these conclusions have important consequences in phenomena like refraction, shoaling, and wave and current interaction.
There exist some important very visual interactions that affect the way waves develop and transition into their breaking stage. Firstly, as the waves approach to the shore, seabed friction becomes a bigger factor. In fact, the energy lost due to seabed friction produces an apparent decrease in velocity, and as wave moves more slowly, they tend to bunch up, creating bigger bodies. This phenomenon is called shoaling. Actually, these energy losses can be estimated using Airy's linear wave theory, obtaining a mean seabed stress of 1/2 the friction factor times the density times the squared of the mean velocity near the bed. Moreover, it has been proven that this friction factor depends on the rhythm of the flow and the roughness of the soil, very much like in the case of the flow inside a pipe. And just like we have Moody charts in that case, we can find Dyer diagrams for wave movement. Friction not only modifies the speed and height of the wave, it also modifies its direction. As waves approach an irregular shoreline, they tend to steer away from deeper waters and towards shallower waters, therefore attracted towards headlands. This phenomenon is called refraction. Another important interaction happens between sea currents and waves, since currents positive in the direction of the movement increase the frequency as they add up to their velocities. However, currents in the opposite sense add mass flow and contribute to the circular movement pattern explained in the beginning, increasing their height. When these two factors combine in big expanses of open water where winds can affect, waves can grow into terrifying tsunamis.
Up to this point, general perception of how a wave is created, how transmission and movements towards shorelines occurs, and a review of the important phenomena involved in all has been done. It is time now to be more specific until reaching the breaking point of a wave. So, when a wave is broke, there are two criteria that estimates when a wave will break: wave steepness or the wave height water depth ratio, being the limit around 0.8. Once a wave breaks, how will it break? To estimate the way of breaking, the dimensionless irregular number is used. If its value is less than 0.4, a spilling break will occur. White water appears at the wave crest and spills down the front face, sometimes preceded by the projection of a small jet. If irregular number is between 0.4 and 2, a plunging break will occur. Most of the wave's front face overturns and a prominent jet falls near the base of the wave, causing a large splash. If the number is higher than 2, two possible breaks could occur: surging, where no significant disturbance of the smooth wave profiles occurs except near the moving shorelines, or collapsing, where the lower portion of the front face overturns and behaves like a truncated plunging breaker.
Describing breaking qualitatively, here we can see how a wave crest is projecting in an overturning jet and then splashing onto the water surface. The rotational fluid motion within the jet that surrounds the air tube governs the flow. As it is easy to notice, the wave crest is highly unsteady. When using the approximate methods available to define this, they fail, sometimes leading to singularities. However, we do know that accounting when and how waves break is entirely in terms of implicit initially irrotational flow, without concern for the air above the surface or surface tension. The process before reaching the plunging point is what we understand with overturning. There are three relevant features for this motion. Here, water particles' velocities exceed the phase velocity of the steepest wave. In front, water accelerations exceed gravities to accelerate the water that is projected forward in a jet. Beneath the backslope of the wave, water has low accelerations, ensuring the high pressure gradients necessary to produce the acceleration in the previous region, thanks to hydrostatic pressure and wave asymmetry. Let's see it this way. The dynamic boundary condition at the free surface is weak, so acceleration is due to the water's inertia and gravity. The kinematic boundary condition is that the surface is a material surface and moves with the water. In velocity fields, material surfaces become very distorted and folded. Then, describing overturning is a key for breaking, but these dynamics don't provide with times, although approximations for shapes can sometimes be studied.
Once the jet from an overturning wave hits the water at the plunge point, water splashes up, sometimes to a height greater than the original wave. From the plunge point onward, the breaking process appears to degenerate rapidly into a chaotic motion of air and water. However, close and careful inspection often reveals a surprising amount of order within the wave. A misleading impression of the flow is easily obtained, since in any one direction a single drop or bubble is sufficient to interrupt a line of sight. The splash-up commences from the plunge point. At the present time, only a few visual and photographic observations of the splash-up have been made, and its mechanism and the origin of the water in the splash up are not really clear. The water must come partly from the jet and partly from the previously undisturbed water. The division might be even or tend toward one extreme. Most breaking waves settle into a quasi-steady state after the plunge point and any ensuing plunge splash-up cycles.
Now that we have seen the theoretical part underlying this phenomenon, it would be interesting to perform a real experience. There are experiments that imitate waves pretty well, such as this one using a water tank and a pushing plate. However, given the lack of media, an alternative is needed. So we have decided to make waves break through a CFD simulation. Let's check how. First, a control surface is defined for the fluids, with a simple rectangular geometry of 10 meters length. Secondly, the surface is meshed. To get a very accurate result, it was redefined, imposing a maximum cell size of 5 centimeters. Next, the boundaries were named. On the left, a velocity inlet, on the right, a pressure outlet, on the top, atmosphere, and on the bottom, a wall. It is a transient simulation in which we have used K-OMEGA-SST turbulence model, as well as the multi-phase model so water and air can be defined. For the boundary conditions, it is important to highlight that Airy equation rules the inlet with a given amplitude and a wavelength. After initializing, the domain reveals a steady amount of water on the bottom in blue, and on the top there's air in red. The calculation starts, and when every time step converges, this is the result that we obtain. The same procedure is applied to a domain with a tilted bottom, and finally, the wave breaks.
After watching the video, we have learned what a wave is. We have obtained their mathematical description, the energy equation related to them, as well as the celerity to compute it. Also, friction losses have been studied, and the simulation, assuming all the errors that making a CFD leads to, has been shown. Along with all this information, breaking point, type of breaking and breaking process has been developed and explained. We have just started to know the great creation of nature, the waves.